Welcome to the next video in measure theory and probability. This is video 13 on exercise 1.5. This is part 1, chapter 1 of the textbook. So here's the exercise. Suppose we have a measure space and the mass of the measure is positive. And suppose that we have a measurable function f, and it goes from E to R. We will show that for every positive real epsilon, there exists a measurable set such that it has a positive measure and the distance between f of x and f of y is less than epsilon for every choice of x and y in our measurable set. Okay, here's a first naive attempt. So let's set epsilon to be some positive real number. And since it's hard to think of, what measurable set in the range we should pick, but it should probably have something to do with epsilon, then maybe let's just arbitrarily pick negative epsilon to epsilon and see what happens. So we certainly want to take its pre-image because f is measurable and that is, any interval is a measurable set, then the pre-image is measurable. So that's great. That seems like progress. We also have that if you pick any x and y from the pre-image, then it will happen that, not that it will happen, but that by design, those will fall in between negative epsilon, and therefore the distance between them will be less than epsilon. So hopefully all of that makes sense. What's missing, right? This can't be the full proof. Well, we certainly have no necessary reason to think that the measure of this particular set, right, this pre-image, is positive, right? So we're missing this feature. How do we guarantee that we do this, but we get a measurable set that has positive measure, right? Well, we haven't used the fact that the total mass is positive, and that seems like that should be relevant. And also, this is just arbitrarily centered at 0, which seems like not not an essential part of this problem. So somehow that seems wrong. Okay, so maybe the idea is that we need to not just do this arbitrarily at 0, but maybe we need to kind of scan through all of the real numbers, maybe breaking it into pieces of size epsilon, right? So here we're taking the interval from, epsilon times n minus 1 to epsilon n, right? So this interval has width epsilon. And since we sort of take this over all possible choices of integers, then this will basically just kind of break the number line into pieces of size epsilon. Now we have that the pre-image of the entire real numbers, well, that's just the domain of the function, which is E, and that has positive measure. So maybe if we take the measure of the entire pre-image, right, all the pre-image of the real line, then we take the real line, we break it into pieces like we've indicated here, and then because this is a disjoint union, probably I should have even written it as a disjoint union, then we can apply sigma additivity. It's a countable union too, by the way. And so that effectively gets us a sum of all the individual measures. Now here I'm writing that sum just so that we've got the numbers going from, this is the interval from 0 to epsilon, right? Because n starts at 0. And then it goes from epsilon to 2 epsilon and so on, right? So this is kind of like going out towards the positive direction. And this, this is like negative epsilon to 0 when n is equal to 1. And then it's, negative 2 epsilon to negative epsilon when n is equal to 2, and so on. And so this is the portion that like goes out towards negative infinity, right? But the important point, right, that's all just sort of like accounting for technicalities. The important point is that we get this sum over all the measures of those intervals, or the measures of the pre-images of these intervals. And look, this quantity, as we already established, is positive. Well, if, each of these is non-negative, right? So if a sum of two non-negative things is positive, then at least one of them must be positive. And then, long story short, this entails that at least one term somewhere here must be positive. And from there, we're basically done, right? We've basically, whichever term here is positive, we have that if you pick any 2 point, like that is our measurable set, right? This pre-image of this particular interval is the measurable set. If you pick any two things out of it, their distance is no more than, or strictly less than epsilon. So there's the solution.